Welcome to the first and only bioengineering project this semester. My name is Sohaib Akhter. I'm the project manager. This is Junaiden, Samir, Francisco, and Shiful. And our project's title is the Android-based Haptic Vision-Substitution System. I know it's a mouthful, but it accurately describes our project. For simplification, we call it the iPhone project. Okay, so the introduction to our problem, the problem that we're addressing is that blind people can't see. And, and this affects 39 million people worldwide. So what alternatives do they have to actual sight? They have guide dogs and and white canes, which don't improve their visual perception. It only gives them the ability to avoid collisions. And they also have this audio feedback visual aid, which gives them the distances of objects around them, but it obstructs their ability to hear. So that will give them key information of their environment and their surroundings. So our solution was to use, as you remember the title, Haptic Vision Substitution. So haptic is a tactile feedback. We're using the sensation of touch to relay the information of the obstacles that are around the user. The requirements of this system is that it should be reliable, lightweight, durable, and improvable. We want to make it customizable for every user. This is the inspiration for the project. I don't know if any of you know this, but this is the witch from the Clash of the Titans. In mythology, these witches use an external eye to see their surroundings. So we were planning on replacing that with an Android smartphone that can do that. That's a catadioptric stereo rig, which we'll go into in our further slides. Just to show you how interesting this project is, we actually got a publication on this in the Northeast Biomedical Engineering Conference. So now I'll turn it over to Francisco for our system architecture.
All right, this is our level 1 system architecture. The catadioptric stereo rig captures a left and right image and then is processed by the Android phone, and that is sent to the microcontroller, and that is sent to our vibral tactile matrix, which gives the user a tactile stimulation. In more detail, the Android phone computes stereo correspondence and compresses that to an 8x8 integer matrix, which is sent to the microcontroller via Bluetooth. And that our microcontroller controls the motor drivers and demultiplexers on our vibral tactile matrix.
So one of our tasks was to make a catadioptric stereo rig. The purpose to make a catadioptric stereo rig is to get a left and right image for the stereo image processing. In order to make a catadioptric stereo rig, we had to do a bunch of calculations. First of all, we found the focal length and the angle of the lens of the camera. Once we got the focal length and the dimensions, for the simplification, we used angle between the inner mirror and the base of the frame to be 45 degrees, and we separated the inner mirrors and the external mirrors to be 20 millimeters apart in order to get the better depth while still having the frame on the phone. Okay, then we have to do more calculations. Once we got an angle for the internal mirror, then we calculated the angle for the external mirror in order to get the frontal parallel computation. Using basic trigonometric equations, we got these results. Once we got all our specifications, next thing was to implement the stereo rig. We had to cut and file the mirrors in order to match the specifications, and then we glued those things on the plastic and the balance of wood. And this was our final result as a catadioptric stereo rig.
Okay, so once we received the frame from the catadioptric stereo rig, the first part of our Android image processing code, which we implemented in OpenCV, the computer vision C++ and C libraries, was to segment the left and right image from the frame. So it's a simple crop. But then after that, we have to, our algorithm does two processes. If it's already calibrated, it'll go on to the next step. Otherwise, it'll calibrate it using a number of images of chessboard corners, and it uses that to find intrinsic parameters of the cameras. So, and then after it receives these intrinsic parameters, these parameters can go onto a transformation matrix, which will map one of the image onto the other using affine transforms. So then we rectify the images using horizontal epipolar lines, epipolar geometry to condense our two-dimensional scanning problem into a one-dimensional scanning problem. After that, we use a sum of absolute differences filter, which will find a specific point on one image and map it to a corresponding point on the other image. The distance between those images in terms of pixels is will be used to compute our disparity. So we do this over all the pixels in the image, and we come up with a disparity map. And then from that, we just crop it, resample it to an 8x8 integer matrix, which we send to our vibrotactile array over Bluetooth. And now microcontroller go.
All right, the microcontroller we chose was the Arduino BT, and we chose it because of its quick baud rate and the ease of programming it. Here you can see a flowchart for the code that we programmed into the microcontroller. It listens for an array. The values in the array correspond to values given to intensity values given to our vibro motors. When the data is received, it's stored onto in a buffer, and the buffer is parsed to our vibrotactile matrix. And this, when the data is received, the serial is flushed, and it continues to listen for an array. And then here you can see visual output of our code in the form of an 8x8 LED matrix.
Next is power management. We chose rechargeable PSP battery to power our circuit. We tested different component of our circuits, and we estimated that total usage current is 485 milliamp current. Therefore, that it will last our circuit up to 5 hours. Next is the voltage requirement. For our system, it requires 5 voltage. As you can see, PSP battery gives us 3.6 volts, which is not enough for our system. Thus, we're required to boost up the step-up switching mode power supply. So we use Maxim 1674 chip to boost up our system. The reason we use it because it's 95% efficiency at 500 milliamp current with 5 volts. The next is, as you can see, our schematic of our power circuit. Also the graph of efficiency versus load current. With 5 output voltage, it gives us maximum current of 500 milliamp, which is enough for our circuits. The next is we breadboard and tested the circuit and got our results steady state error to be plus or minus 0.3 volts. And this is our final vector board design. The next, Junaiden will talk about vibrotactile matrix.
Vibrotactile matrix as our main board for our project. It basically consists of we used the TLC 5490 LED driver chips along with this small this coin vibration motors, and to make our 8x8 matrix. As you can see, the vector board and Arduino board together, they're in this pouch, and there's the motors, 64 motors. Let's get as 8x8 matrix on upper back user. The TLC chip, each pin gives a proper output current, to drive our motors, and we chose the Shiful coin vibration motors because it gives a good haptic feedback on the skin. We then daisy chained 4 TLC chips to drive our motors, and these are the Shiful coin vibration motors, and this is the TLC chip, and the motors connected across the smoothing capacitor and a snubber diode to even up the sharp pulses on the pulse width for pulse width modulation from the TLC chip, and the snubber diode evens up, prevents the inductive kick. Then the components soldered into vector board, which is in the pouch, and then the motors swung into a microfiber compression t-shirt for user to feel better feedback. We had 2 different testing, latency and acceptance testing. For latency testing, we had 3 trials. We want to see how fast the data can be sent. For image processing, we found that it took about 89 milliseconds to send a single frame. Since we're using in the Android phone, the image processing in the Android phone was about 89 milliseconds to send a single frame. Since we're using Bluetooth 2.1, both in the Android phone and Arduino board, with 2.1 megabytes per second frame rate was too fast to determine, since we're sending only 64 bytes. Arduino parsing to the 8x8 matrix was about 5 milliseconds for a single frame to be sent. So 10.64 frames per second was our frame rate. Next, we did our acceptance testing. It was done by based on collision avoidance and object detection. The collision avoidance, where the user walks on the hallway, see if he hits the wall or not. Object detection, basically, the user will identify 4 objects on the table. As you can see, for the collision avoidance, we had 8 trials, 2 subjects, and we achieved 87.5%. For object detection, we had 16 trials, 4 subjects, and we achieved 62.5%. The collision avoidance rate is higher than the object detection, just because for low vibration, the user would be able to know the objects around and could avoid the collision. That's why the collision avoidance is higher than the object detection. Also, the vibrotactile array mass is about 1.3.4 pounds. And next, we'll show the video to even more prove this testing.
Next is the administration section. You can see the total funds amount we spent throughout the project, excluding the Android phone and Arduino board, because Sohaib just temporarily donated. The total amount of money we spent is $392. Also, the man hours each group member put into our project, and member contribution. Sohaib Akhter, he was the project manager. He did the documentation and Android code and image processing. Francisco did Arduino code and vector boarding. Junaiden did the circuit board and vector design, vector soldering. Sareen did the cardiac story rig and the system testing. Myself, I did power management and financial. The next is acknowledge lesson learned.
Okay, so we learned a lot during our project. We can break them down into teaming lessons and technical lessons. First part of teaming lessons is always have patience and persistence. This also goes for the technical lessons because some of your circuits are stubborn. But when your colleagues are stubborn, you gotta just be patient with it and try to work through the problems. Because if you create some tension between your team members, obviously have some, it'll propagate throughout the rest of your project. So always maintain good communication and instruction. Make sure everyone knows what they have to do, and that if they have a problem, they can come to you. Distribute the tasks evenly. Make sure that one person doesn't have a lot to do and someone else has very little to do. Hold those weekly meetings. It's important to, when you're with other classes, you kind of lose track of where the project is. So the weekly team meetings help you to keep track of that. Always ask for help. We have faculty around us that have great experience with a lot of issues that we have, so we can always ask them for help, have some more brains think on the project. The technical lessons are, one, order twice as many parts because parts break and they burn, so it's better than waiting a couple of weeks for shipping to have all the parts that you need. And build circuits stepwise, because if you build the whole circuit in one go, then you realize if there's a problem in the circuit, you don't know exactly what component caused the problem. Whereas if you built it stepwise, you would have figured out, oh, this is the problem, let me fix it. Next, set aside a week to set up a programming environment. If you have a large software project, make sure that you know how to compile your project, port it over to whatever devices you need to port it over, because that takes a long time to do. Don't underestimate it. Also, check and test after every step of your project. You do a unit, make sure that you do the unit testing for it. We'd like to thank a few people. First, Dr. Pakowitz as a faculty supervisor, my mom for sewing the vest, and for you all for listening to our presentation. Any questions?